Good day. I'm Professor Rushan Zadinov at Keimyung University in South Korea, and today I will present the following topic entitled Class F Curve Modeling in C3D FairCurveModeler. So first of all, C3D FairCurveModeler is a library for smooth curve modeling that extends the surface modeling capabilities of the C3D modeler geometry kernel. It's implemented as a whole new part of the C3D modeler geometry kernel. Besides generating high-quality curves in terms of fairness, its algorithms ensure the following advantages, such as flexibility, sustainable shape generation or isogeometricity, suitable for isogeometric approximation of analytical curves that preserve their basic features, invariance under affine and projective transformations, as well as a wide range of applicable tools. So, what is a smoothness? This definition is related to a smooth function. A smooth function is one with continuous derivatives up to a certain order over a given domain. Over a given interval, such as from A to B, a function can be considered to be smooth. The number of continuous derivatives required for a function to be deemed smooth varies from 2 to infinite depending on the task at hand. Smoothness is a property of a function or a curve or surface indicating that this function can be differentiated or that each point of the given curve or surface has surroundings that can be defined using differentiable functions. Different types of design use splines of different orders of smoothness. For example, when designing rod roots, clotoid splines are used and smoothness of at least the second order is ensured. For profiling the camshaft cam of high-speed engines, smoothness of at least the third order is required. Therefore, the profile design begins with drawing a smooth graph of the third order derivative. To ensure continuity of the torsion function when modeling space curves, the curve must have third order smoothness. A space curve with smooth torsion should have fourth order smoothness, which follows from the analysis of the spatial curvilinear trajectory of the point particle. Only spline curves of the fifth degree or higher, at least fourth order of smoothness, provide a smooth change in torsion and can be used to model functional curves. A surface can be drawn from a network of plane curves. Therefore, planar or space curves in the curve network must also have a smoothness order of 4 or higher. Based on the analysis of point particle motion along a curved path, requirements for the quality of functional curves are proposed. A high order of smoothness, a minimum number of curvature extreme, minimization of the maximum value of curvature and its variation rate, minimization of the potential energy of a curve, and aesthetic analysis from the standpoint of the laws of technical aesthetics. We do not set ourselves the task of giving a simple and precise mathematical definition of such curves. On the contrary, this category can include various curves that meet certain quality criteria, the refinement and addition of which is possible in the near future. Engineering practice shows that quality criteria can change over time, which does not diminish the need to develop multi-criteria methods for assessing the quality of geometric shapes. Based on the above, Class F curves have strict requirements for fairness criteria. This is precisely how they differ from so-called Class A curves. The next question. So why our approach is totally different from other existing approaches? The aesthetic attractiveness of industrial products is critical to their market success. Curves in industrial design must meet aesthetic standards since the characteristic lines of an industrial product are particularly significant for its aesthetic impact. Polynomial and rational parametric splines are utilized to create the majority of curves and surfaces in traditional CAD systems. However, for highly aesthetic criteria, certain curves and surfaces, such as NURBS, may be insufficient. One of the problems is that controlling the curvature is still challenging. So unlike many other works, where authors are usually focused on one or two quality criteria, we offer a multi-criteria approach to the assessment of the shape quality of curves that constitute component parts of the surfaces used for the computer modeling of object shapes in various types of design. The next question arises, so why class F curves but not class A curves? So as you can see from the given pictures, generating a B-spline from given set of points on a circle by using Siemens NX software on the left and C3D FairCurveModeler on the right illustrate the difference between Class A and Class F curves. As it can be seen, Class A curves do not provide a desired performance. So methods for Class F curve modeling include the following. First, generation of the Hermite data and determination of inflection points. Second, breakdown of a curve into separate locally convex areas. Third, creation of virtual curves or V-curves. And fourth is isogeometric approximation of virtual curves. So the math behind C3D FairCurveModeler is based on parameterization. So with it, we generalized the concept of the spline as a set of curves having equal geometric parameters at arbitrary points on the base polyline. So in conventional splines, the parameters of the curves are equal only at the spline's segment junctions. So the first innovation is that the basis of spline definition is a set of double osculating conic curves on a locally convex base polyline. The adjacent curves form a lens on the polyline segment they share. The spline tension is characterized at the deviation of the adjacent analytic curves of the basis spline. It can be easily assessed visually by the size of the lens between the two adjacent curves. The second innovation in the algorithm that generates the virtual curve or V-curve on the basis of a spline constructed with a discrete set of a double osculating conic curves. We developed the V-curve method with some notable features. So it offers the lowest number of curvature extreme values. This is the first. The second is it exhibits duality because the V-curve can be defined both with base vertices and tangents, just like conic curves. Third, it has a fine invariance. Fourth, it presents low sensitivity to the vertex distribution along the curve. And the last one is the curve vertices that are generated in the lens area reduce the tension of the resulting spline. Then we redefined a set of double osculating conic curves on the set of the generated vertices. A sequence of these operations at the limit defines a C5 class virtual curve. These features enable geometrically accurate modeling of conic curves. Let's have a look on the following example. So on a uniform grid, we can create a virtual curve and approximate it with a B-spline curve of degree 8. The option to harmonize the distribution of points on the virtual curve is utilized while designing a virtual curve. So in this case, radial runout error is 6 times 10 to the power of minus 7. So it's very, very small. Modeling a B-spline surface in C3D FairCurveModeler starts with a set of polylines. A high quality of a surface is ensured by the construction of virtual forming and directing curves of the surface. In this example, the vertices of the polylines belong to a torus. The right picture shows an image of aligned surfaces, the torus and the B-spline surface. So now let me talk you about the applications of such curves. So the applications of class F curves and surfaces are shown below. These include tillage implements, aerodynamic profiles, external surfaces of aircraft, ships and cars, profiles of compressor and turbine blades, and also propellers. On this slide you can see a model of a steam turbine blade profile. Instead of a local spline represented by circular arcs, we use a virtual curve constructed on a tangent polyline. So this model was tested in the Compass Flow simulation software. Comparative tests show improvements of the average exit speed and a total outlet pressure, so 1% and 3% respectively, as shown here. C3D FairCurveModeler is a good choice if there is an interest in designing aesthetic shapes. Due to unique methods of approximating analytical curves, we can easily import so-called logoaesthetic curves into our projects. It's important to note that a wide class of fair curves can be generated by using superspirals, which are curves of monotonic curvature function defined in terms of Gauss hypergeometric functions. Moreover, C3D FairCurveModeler integrates unique methods for constructing composite curves up to the 9th degree of smoothness. We can also generate monotonic curvature curves from two given points and tangent directions in these points. So my request is, please try class F curves. Among other advantages, they are mathematically beautiful. At this point, I would like to finalize my presentation. Thank you for your attention.